Problem number 2. Excuse me, I'm running out of voice. Nonlinear spring, so this doesn't follow Hooke's law, which is interesting, is compressed various distances x, and the force required to compress it is measured for each distance. Data shown in the data table below. So we had, I've already started filling it out. You can see that there, but we had our x values and our force values. Assume the magnitude of the force applied by the spring is in the form of f of x equals a times x squared, which is really nice because that basically answers the next question for us. Which quantities should be graphed in order to yield a straight line whose slope could be used to calculate a numerical value for a? So if this is the equation they're giving us, if we plot f versus x squared, it'll give us a, right? That's just like relate this to y equals mx plus b, right? If we put in f for y and x squared for x, the slope of that line will give us a. So we can find a pretty easy. You could have also said, right, to take the square root of both sides, and the square root of f versus x will give you the square root of a. So if you wanted to do it that way, you could do it that way, but that seems more difficult to me. So I was going to do f versus x squared, calculate the values that aren't given. So I needed x squared, which means I needed to calculate x squared. So I just took the x's and squared them. Pretty straightforward there. On the axis below, plot the quantities you indicated, label the axes, and appropriate numbers to indicate the scale. So you can see force in newtons, x squared and meters squared. I've got my line of best fit in there. I've got my green points that were the points that were in the data table. And there's my graph. It doesn't say a title, but I guess I could have put a title, force versus x squared, if I wanted to. It doesn't ask for that though. Maybe we don't need a title. So there's that. Using your graph, calculate a. A is going to be equal to the slope of the graph. Unless you did it this way, then a would be equal to the square root of the slope of the graph. Whatever. Or a would be the slope of the graph squared, I guess, is how that would be. A would be the slope of the graph squared. But the way that I did it, slope is just equal to a. So I picked 2 points and I calculated the slope. For this one, you didn't get points for the way that they explained it in the solutions. All these green points are supposed to fall directly on the line. I think they set it up so that those points should fall directly on the line, which means this blue line that I have should be we should have a perfect relationship. There shouldn't be like any points above the trend line or below the trend line. They should all be right on the trend line, which means you could have picked any of the points that we already had and used those. But I think best practice is to always choose 2 points that are on the line that are not given points, because there are graphs that they give you where the trend line just goes through the middle. And if you don't choose lines or points that are on the line, you lose points, right? If you picked points that were given, you would lose points because they're not supposed to be on the line, or they're not necessarily on the line. So I think best practice is always to choose 2 different points, not points that are given or points that are in the data set. So I picked just 2 random points on my line that I thought were pretty straightforward, pretty clear. And I used those to find the slope. And I got 1,750. If we're looking at sig figs, which sometimes we do, and this problem they did look at sig figs, is 1.7. If we look here, everything in my table is 2 sig figs. So I probably should have kept the graph in 2 sig figs as well. I didn't. But we could answer that in sig figs with just 2 sig figs there. Spring is then placed horizontally on the floor. One end of the spring is fixed to the wall. Cart of mass 50 kilograms or 0.5 kilograms moves on the floor with negligible friction. We don't have to worry about friction. Collides head on with the free end of the spring, compressing it a maximum distance of 0.1. So our cart collides into the spring. Calculate the work done on the cart in compressing the spring. So this one was a little bit harder because our force is variable, right? In mechanics question number 1, we were calculating work, and we got to pull force out because it was a friction force and it was constant force. This force is not constant. It varies with x squared. So we do have to do the actual integration here and plug in ax squared for force. Integrate, the a pops out. We get the integral of x squared dx, which is x to the third over 3, evaluated from 0 to 0.1, because that's our distance there. We plug in, and then we've just got something that we can solve, right? We solve for the a value in part D. That just close that hole. I minimize it. Whew, thank goodness. The 1.7 times 10 to the negative 3, 10 to the negative 3, 10 to the positive 3. Stop that. And then we solve. We get the work of 0.57 joules. Calculate the speed. Work is equal to the change in kinetic energy. The ending kinetic energy is 0 because it's pressed up against the spring, and that was it said it's the maximum compression. Yeah, maximum compression. So all the kinetic energy is gone, which means the work will be equal to the initial kinetic energy. So we set work of 0.57 equal to the initial kinetic energy, 1/2 mv squared. We have the mass. We just need to solve for v squared, and we get v is equal to 1.5 meters per second. And there is 2006 number 2.